All right, hello everyone. Last time we started talking about friction. I just started talking about friction, and what I mentioned is that friction as a force, which we neglected initially, it's not so intuitive, and we need to think about some of the details. So today we're going to go through some of these details. So today's lecture is about friction. We're going to start with an example. Before I start, I want to give you something to think about. Now, as we started to think about friction, which means things that we see around us now, as we observe them, objects that move, they don't keep on moving. So if I push some objects on the table here, if I elevate this table a little bit in front of me, you'll see it, the table here. If I start pushing objects on this table, then there would come a point where they would stop, right? They won't move forever. And part of that is, well, now we know it's because of the friction force, which we're taking into account. So our calculation is becoming more realistic in that sense for these type of problems. We discussed two different types of friction. We said that if there's an object and that object is stationary and you just start pushing it, it's harder to make that object start moving. But if the object is already moving and you're helping pushing it, or you keep pushing it, then it's easier for that object to be pushed. And we said there are two coefficients for the friction. So there's mu is the friction coefficient. You see that? Okay, looks fine. So mu is the friction coefficient, and you can have either mu s for static or mu k. So this is if it's moving already, and this is if it's static and you want to make it start moving. So mu s is always larger than mu k. So the example I want you to think about is if you have a car. So you think about cars and think about tires. Why is it that the race cars have very large, wide tires? I want you to keep that thought in the background of your mind as we develop through the lecture. Okay. It is related to friction somehow, but how is it related to friction? Is it because of the surface? The surface is larger. What is the reason behind that the tires are larger in, especially in racing cars? Okay, so let's start with the example. We have an incline, and we put an object on the incline. The object is here. Oops. And we want to know what would happen to this object, given that we have friction now in the system. The first question that should come in mind, what type of friction do we have? Do we have US, or do we have F, do we have mu K? And the most difficult part actually about friction is that we don't know. You tell me if this is moving or not, I will tell you if it's mu S or mu K. So if someone gives you this type of problem and tells you, okay, let's analyze what's happening to this problem, you would say, okay, we have two possibilities. We have more actually, but let's start with two. One possibility, this object is just standing still, which means what is important is mu s. You make your analysis according to that coefficient. Another possibility is that this object is accelerating downwards. In that case, you would have a friction, which is the coefficient in mu k, and the friction would be in the opposite direction. The friction is always in the opposite direction. The friction force is always in the opposite direction of the movement. But there's a third possibility, really. What if this object is actually has some velocity in the uphill direction, so in this direction? So it is decelerating, right? Which means that there would be some time, and listen to this carefully, at the beginning, because you know it's moving, it is mu k, but the friction is in the downwards direction. But there would come some point where it would stop, right? It is decelerating, and then the velocity would just come to zero at some point. And at that point, exactly when it stops, you would have to deal with mu s. If it starts moving downwards after that, that necessarily depends on the forces and the friction coefficient and so on. But this might be part of the question that you have. If it as it starts moving downwards, then you know, say, okay, the friction now, for the friction force has to be in the opposite direction now. So I make the analysis with the opposite direction, and I make the analysis using the coefficient, which is mu k and not mu s. Okay, so let's take it easy. First of all, whatever you do, you need to decide about the coordinate system. How do you decide about the coordinate system? You can choose any coordinate system that you want. However, I would highly recommend that you would choose the coordinate system in a way that the y-axis, if you take x and y, so the y-axis is in the normal direction in this type of problems, which means you don't need to worry about the forces in the y direction, right? It's not moving anywhere in the y direction. And you would only need to worry about forces in the x direction. Now, whether you take the plus x in the downward direction or in the upward direction, that's up to you. And does it really matter? Whatever you get at the end of the day, if I take it downwards and I find out that, well, I don't find out, you'll see that I would have to assume first in order to solve it. So you need to be careful. So let's assume that this object is actually traveling downwards. All the forces that this object has, they have gravity. So we have mg. We have a normal force, m. And we know it's traveling downwards. So we know that the friction force has to be in this direction. It's opposite to the propagation direction. So this is the F, the friction force. If I want to talk about the moment that this object is just about to start moving downwards, okay, it's not moving yet, it's just about to start moving, then I will have to talk about mu s. And I remind you that the relation, so for the force, friction force, the maximum friction force is mu times m, the normal force. And in this case, I'm going to write this in a second, but let's look at the decompose the gravity here, gravity force. So we have one in the x direction and one in the minus y direction, right in blue. So we have mg cosine, this is alpha by the way, and this would be mg sine alpha. We decompose this vector. And we know that mg cosine alpha has to be equal to m, like it's not accelerating anywhere in the y direction. So this has to be equal to mu s. Why mu s? Only because we are analyzing the scenario which is just about to start moving. Okay, I'm going to write this here. Just about to start moving. It's not moving yet, it's just about to start moving, and that's why it's mu s times n. What is n? It's mg cosine alpha. All right? I remind you that we are solving the problem when the object is just about to start moving. So we can write now from Newton's second law. From Newton's second law, mg sine alpha minus f of f. So we have mg sine alpha minus the friction force. That would be the maximum friction force, right? Equal to 0. So mg sine alpha minus mu s mg cosine alpha equals to 0. Now look at this. We lose the m here and the g. We lose the m and the g. You can understand why you lose the g. I hope you do, right? It's like the gravity is acting on everything in the same way. But we have the m here, which we lose as well, and we end up with the following, that mu s equals to tangent alpha. Very simple. Mu s equals to tangent alpha, which is also very easy to measure. I have here this measuring device, which I can adjust. This side with the angle. I can put an object on the on one surface, and I measure the alpha of that object when the object starts moving. The alpha of the surface when the object starts moving. And just by using this equation, I can compute the coefficient, the friction coefficient. But let's not hurry up. Isn't this strange? Isn't it strange that the friction coefficient is only related to alpha? It has nothing to do with the mass. You can put as much mass as you want. What really matters is the type of the material. It's the molecules. It's the what is called molecular compressibility between the object and the surface. It doesn't matter how much mass you have. It doesn't matter what is the width of the object. It doesn't matter what is the width of the tire in the racing cars. So, which brings me again to the question of why do racing cars have wide tires if it doesn't really matter for the friction coefficient, the size, the width of the object. Take a very narrow object and take a very wide object, as long as the material is the same material, in theory, and not only in theory, if you make a careful experiment, then they should start sliding together. Can you repeat the question? I could not manage to see it. Okay, let me check. What does it? This is a very important question. What does it say in the? So you can't see this well. Let me bring this forward. So. This better? Okay. US equals tangent alpha. This is my tangent. This might be the. This is my tangent. Okay. TG is TAN. This is my tangent. Okay, so mu s is tangent alpha. You see this from here, right? Mu s equals to sine alpha divided by cosine alpha. All right. If that was only equal to, I will move this back. To have more screen. Okay, so now we have a way of measuring the objects, as they're sliding. So we can measure the inclination, and from the inclination we can find out the friction coefficient. Mu s is the friction coefficient. For example, if you have a car, just to let you know what physically does that mean. If you have a car and that car is on an incline, okay, if the friction coefficient mu s of that car, which sometimes you can see on the tires, I guess, is equal to 1, it means that tangent alpha equals 1. It means that the maximum inclination that it can be before start sliding would be 45 degrees. Okay. I can show you some very, very qualitative demonstrations of the this problem. Cannot even guarantee that it would work. So I have the surface here. This is the surface. I can put objects. Let me put this a bit down so you can see better. So I can put objects here and start inclining the table. I can even measure the angle using this device. In fact, I can measure the friction coefficient that has to do with this device at this surface. Friction coefficient always has to do with the two surfaces. Okay, it's not only one. It's not only the object, but the object and the surface. So if I put this here, all I need to do is start inclining it. At the same time, I need to find out the angle. It just started moving. So this is about it. Okay, a little bit more. Okay, it started moving, and this is telling me about 12 degrees. Okay, about 12 degrees. So the alpha is 12 degrees. If you take the tangent of 12 degrees, you should get the mu s of this object with that surface. You might have noticed that it would start sliding and then stop and then start sliding and then stop. I said it's very, very qualitative demonstration because the friction coefficient is very sensitive to many things like the humidity, the temperature. This surface here, I can see that in some places is very dirty. It has dust, right? So that affects the friction coefficient. In other places, you have dust more here and here. And you have so the distribution of the dust is not homogeneous, but also there might be some humidity maybe, and other factors that would also can really change the friction coefficient. So it's not very easy to measure it precisely. Okay, now let's carry on. I can show you also if you, let's see if it works. Get here a box. Get another box here. So the green box is empty. It's supposed to be the same type of box. Some spot on it. The yellow box is not empty. It has all this paper, so it's quite heavy actually. I can put them next to each other. In principle, right? So they are next to each other now. This is the empty, and this one the heavy. Okay. Now, in principle, they are both made from the same material, but as I said, the table is not clean, and that would affect the race. But in principle, if I let them race, they're supposed to start moving more or less at the same time. Okay, so this is the heavy, this one is the heavy, and this one is not heavy. I start inclining. More or less. That wasn't too bad actually. I can use now different types of objects. For example, this is more like a rubber. I can try these two together. Now, for some reason, yeah, it's completely different μs for both of them. These two are metal. The surface is not important, as I said. So whether only a little bit. Bernard, would you take over and I will resume in a few minutes. I'm going to change room. Okay, I apologize for everyone.
Yeah, that's fine. Okay, so hello everybody. So first of all, did anybody have any question about the exercises that I sent you guys? Or do you have any question related to the lecture today? Feel free to ask anything. Otherwise, I might start solving the exercises. .1, okay. Is that everything? Okay. So in that case, you will have to wait until I reach that problem because I might start by the top exercise, which is the question 5.29, which says, do you all have the exercises, guys? You don't understand how mu is related to alpha, how the friction coefficient is related to the slope of the surface. Okay. So let me try to get some intuitive. Oh, someone stole all the. I didn't count on this. Okay, I'll try to do it with this. Okay. So basically, what you have to understand is that if you have an object and you have friction, this friction is gonna act parallel to the surface, okay? So as long as the friction acts parallel to the surface, it's gonna be related to the angle of the mentioned surface. Can you see, guys? So as long as you understand this relation, you should understand why is the tangent of alpha. And if I don't know what's the problem with that, okay? So this is alpha, or no, I don't have pens. Amazing. I don't have any way to work this out, guys. I'm sorry. Okay, this works a little bit better. So you have here alpha, okay? And then you have the weight here, right? We just say that the friction force is equal to some friction coefficient, which depends on normally depends on the type of the surface and also on the inclination, okay? So we know that is mu multiplying some normal force, okay? We also know that the normal force is always orthogonal to the surface, okay? And in this case, because the weight mg is not orthogonal to the surface, we have to decompose it, right? We have one component parallel to the surface and one component orthogonal to the surface, right? So this normal force is going to be equal to mg multiplying some angle, let's call it theta, okay? Multiplying the cosine, okay? In this case, of theta. Okay? Do you understand all this, everything that I'm explaining now, or? Yes? Okay. So in that case, you should understand what is the relation between mu and the angle, right? And now you should be able to reach the same conclusion as Osama. Does it make sense? How we relate slowly every force and every angle? Thank you. Okay, wonderful. I think Osama is back, guys. So I will be back with you later. Okay, think about it, and if you have again any question, please ask me later. Okay, I don't mind to go through this again. Okay.
Bernard, I still need a couple of minutes just to arrange.
Okay. Okay, that's fine. So basically, yeah, basically the question is itself in there, right? Do you have any other question, guys? So basically, you have to understand all the laws of Newton: action, reaction. How do we calculate normal forces and how do they act? In what direction? It's always orthogonal to the surface. How to decompose forces, okay? Using angles, okay? So probably this angle theta is related to the slope, right? Maybe it's complementary, right? Once you start applying trigonometry, this is gonna be alpha, okay? And here, this is gonna be a normal angle, okay? So this is gonna be 90 less alpha. We subtract alpha from 90 degrees for this angle, and this is gonna be the complementary, right? For making 90 degrees. So just work on trigonometry, guys, and I will have to try to find some pens. I don't know what happened to them.
All right, I'm back.
Good. Okay. See you later, guys, and good luck.
Okay, thanks everyone for the patience. So we have a few objectives for this, for the remaining of this lecture. First of all, it's so hot in this room. So the objective is to stop sweating by the end of the lecture. It's at least 30 degrees, I don't know why. Okay, which means the friction factor, the friction coefficient would really change a lot in this case. So let's get straight to the problem. Following problem. So I have a similar problem to what I showed you. I have an incline, and we have an object on the incline. And always keep in mind, we always make use of the previous knowledge. Remember that? So we have an object here. And we also now make things a little bit more challenging. This object is connected to another object here. This would be the first object. And this would be the second object. This is a classical example that can show you the difficulty with the friction. We're gonna solve this thoroughly now. First of all, what is it going to happen here? Okay, this is a pulley here. It's a frictionless pulley. Okay, so this is friction on a block with a pulley. We have friction only here on this surface. What is it that would happen here? Let's put the forces first, whatever we can. We know mg acts down here. So we have m2g for this object. We have m1g for the first object. We have T here. We have tension, right? There's a string here between them. And we have T here. Do we have T1 and T2? No. You already know that. We can't have T1 and T2. So T here and T there is the same. In order to solve this problem, you need to know in which direction these objects are moving, if they're moving at all. There are three possibilities. One possibility is that this object is going downwards. As a result, this object is traveling upwards. There's another possibility that this object is actually going upwards, up the hill, and the second object is accelerating downwards. A third possibility is that they're not moving. The balance of the forces is such that there is no acceleration in the system. We have to solve each one of these problems in order to be able to actually analyze the problem. And this is the most difficult part. So if you do that, you should be fine. So now, pay attention. Let's start with the first case. And let's assume in the first case that this object is accelerating up the hill. Which means that, I'm not gonna put it here. I'll write it down here. So first case, the acceleration is up the hill. which means the friction force has to be in the opposite direction. F. And in fact, let's start with discussing the case where the system is just about to start moving, okay? So just as I was saying before, the previous problem, so it's just before it starts moving. It didn't start moving yet, just before it started moving, which means FF would be maximum. Why maximum? Because the friction coefficient would be µs, is the largest. Okay, I'll write this down actually, so no. So the system is about to start moving we need to choose a coordinate system. Now, before we chose a coordinate system which was x in this direction and y is normal to the surface, we always choose y is normal to the surface. So I'm going to choose y here, normal to the surface. But now I'm going to choose x, the positive x in that direction. Okay? It doesn't matter as long as you're consistent. Doesn't matter if you choose x in that direction or in the other direction. We decompose the forces just as we did before. Let's say this is alpha. So we have in the y direction m1 g cosine alpha, and here we have m1 g sine alpha, just as we did before. If the system is at rest and is just about to start moving, if the system is at rest, what do we know from the object? Then T equals M2G. That's easy. Then T equals M2G. You have to keep in mind, only if the system is at rest, this is true. This is the weight, if you remember when we were talking about the weight. This is actually the weight of this object. If this object is going upwards, right, what would happen to the weight? It would go up. It would, if it's accelerating downwards, it would be, what would happen to the weight? It would go down. Keep that in mind as well. These are very simple but important things that you use after you derive your solution, and then you can evaluate and you can find any mistakes that way. All right. So let's go back to this case. So it's just about to start moving, so I can write Newton's second law. What do we have? T on the first object, T minus m1g sine alpha, T minus m1g sine alpha. Don't forget the friction force. Now the friction force is in the minus direction, right? It's in this direction. So it's a minus FF max. Let's write it. FF max equals MA, but as I said, it is not moving yet. So there is no acceleration in the system. So this is 0. In this case, we know that T equals M2G. So I I can write it here. M2G, can bring everything to the other side, equals to M1G sine alpha plus FF max. What is FF max? You know, if you know mu S, you know N. I didn't put all the forces here, right? We have N here. Right? N equals M1 G cosine alpha. So write it here. N equals M1 G sine alpha, should cosine alpha. Cosine alpha, yes. Okay. So we can calculate FF max. So this is the first case, which means that if M2G was slightly larger than this, because this is the critical point, this is the exact point which is just about to start moving, but it's not moving. If M2 was slightly larger, right, than this, and M2G is slightly larger than this, then it would start moving upwards in that direction. This is what this is telling me. However, if M2G is not larger than that, or if it's smaller than this, it doesn't tell me that it starts going the opposite direction. This is the difficult part here. So you have to pay attention to that. I repeat, if M2G is slightly larger than this, the object would start going up, because when it's exactly equal, it's just about to break loose. But it's not there yet. It's static. When M2G is slightly larger than this, the second object would start falling, and this would start going up. If you find that M2G is smaller than this, this doesn't tell you that the object would actually start going the opposite direction, which you would see now. So this is the first case. Now the second case, case 2. Case 2 is that the object is just about to start moving in the opposite direction, which means the friction F max would be in the opposite direction. So I can write now T, now plus here, T, right? T, it's in that direction, plus F max, the friction, Y plus. The friction is also in the X direction. So it's plus minus M1G sine alpha minus M1G sine alpha equals to 0. And you have to remember, why 0? Because the system is not accelerating yet. So now we get, this would be the same. We can find M2, this is M2G, so I write M2G equals to M1G sine alpha, now minus the friction, maximum friction force. I hope now you start observing the differences here. If M2G is smaller, even slightly smaller than this, what would happen is that the second object would start traveling up. If it's a tiny bit, if M2G is a tiny bit smaller than all this, in this case, the second object would start accelerating up, and the first object would start traveling down the hill. And it's not opposite to that case, because you see here there's a plus sign, and here there's a minus sign. Why plus and minus? Because the friction force would change direction, depends on the direction of the movement. So one time is a plus, another time it's a minus. You have to pay attention for that. Okay, the third case is easy. The third case, I have space for it here. So case 3, that's easy. That's the case where nothing is happening really. It's not movement, so no movement, which means A equals to 0. There's no acceleration in the system. All right, let me give you an example using what we have here to emphasize what you've just learned. Oh, is this too far? Okay, I'll do it here. So for example, if we take M1 equals to 1 kilogram, M2 equals to 2 kilogram, and alpha is 30 degrees. And for simplicity, you can take G as 10 meters per second squared. Mu S is 0.5, and mu K is 0.7. You have to shout now. Mu K cannot be 0.7 if mu S is 0.5. Mu K is always smaller than mu S. Mu S is 0.5 and mu K is 0.4. And the question that you have is simple. Is it going up the hill, down the hill, or not going anywhere? To answer that, you have to go through all the 3 possibilities. So let's do that. What do we need for that? We need M2G, and we need to see the condition. Is this condition satisfied? If this condition is satisfied, we know it goes up the hill. If the other condition is satisfied, it goes down the hill. If this condition, if neither of these is satisfied, then it's not going anywhere. So let's see. What is M2G? M2G is 2 kilograms at 1. And M1 G sine alpha, M1 is 1, G is 10. Where's alpha? Okay, so we have 5. So all this term is 5. What is F? F max. Remember, you take mu S. If you do that, it should be 4.33. So the question you need to ask yourself is 20 larger than 5 plus 4.33? Answer is yes, which means it goes up the hill. You're done with that. It accelerates up the hill. Now we have another question. Now this looks easy. I have another question. What is the acceleration? So what is A and T? We need to find the acceleration and the tension in the system. Well, you might say that's quite easy because T is here, right? T equals M2G. But that's wrong. The system is accelerating now. This assumes that the system was not accelerating. So this is no longer right. So to answer that, now you take t minus m2g, f equals ma. We have acceleration equals m2a. So this is one equation. I did that a little bit in a hurry. Let's think about it. We're talking about the case where this goes up the hill, right? So this is going down. If this is going down, then we would write, you have to think this way in the exam, otherwise, and not only in the exam, when you're solving problems. So this is not right. This is the opposite. So it should be m2g minus t equals m2a. However, you might say, well, we have a problem because this is unknown and a is unknown. We need another equation, and for the other equation, we go to the first object. So this was from the second object. From the first object, now we write the same thing we had here, but we have to remember now. You remember when I told you this has to be 0 because there was no acceleration in the system. Now it's not 0 because there is acceleration in the system. So it had the same thing, but this would be MA. Almost the same thing. What else will be different? It's moving now, right? If it's moving, then this friction would have mu K and not mu S. It's not so difficult, actually, all these different scenarios. You just need to give yourself some time to digest all this information. Before we had the case with mu S, everything is static. So there was no F equals ma, A was 0, it wasn't moving, right? Because we were analyzing the case just about to start moving. And for that, we use the FF max, the maximum friction force, which means using mu S. You can't imagine how hot this room is. I don't know why. Now we have movement, which means that F equals ma. We have acceleration. A is no longer 0, but this FF max is basically now not FF max, but the friction force, which uses mu K and not mu S. Just give yourself some time to digest this, and it should be fine. So the second equation, I'm just rewriting this equation now, really. I'm going to write it down there. The second equation that we would have is T minus M1 G sine alpha minus, let's already put it with the, so the friction force now would be mu K times N, and then is M1 G cosine alpha. Still have some space, just as much as needed, equals to M1A. Now we have two equations with two unknowns, T and A being the unknowns. Now, if you solve this equation, and please do that, this is one of the ways to help you digest this problem, you will find that A is equal to plus 3.85 and T is equal to 12.3. What happens if you get A being minus? You might say, well, A minus, what a big deal. This just means that it's accelerating in the opposite direction. But that can be true because when we solve this problem now, we assume that it's actually going in that direction. So if you get A minus, you know that something went wrong in this case. Okay? Because A plus means that it's going down. Let's see if this makes sense. T equals 12.3. Remember, we don't just solve the problems and just get the numerics. We try to understand if the solution we have makes sense. Does 12.3 make sense? What is M2G? What was M2G? Let's see. This is M2G. It was 20, right? M2G was 20 in the case that this is not yet moving. And now the weight of this object is lighter. This object becomes lighter. So the weight goes down. Is this what we expect to have? Yes. So 12.3 makes sense because the object is being accelerated, the second object now, right? Is being accelerated downwards, so it's losing weight. Remember the last lecture. You're accelerating downwards, you're losing weight. You're accelerating upwards, you're gaining weight. So the object here is losing weight, so T has to become smaller. This is a very simple tool to let you analyze what you have and make you decide if anything went wrong on the way. If I had this 20.2 or 30 or 40, I will know immediately that something went wrong because I know it's accelerating downwards. It has to lose weight. So if before accelerating, if it was 20, it has to be smaller than 20. Okay, almost there. It's I'm taking a little bit more time now, but let's finish with this. Now, let's take, I'm not going to solve this completely, but let's take, just to help you digest this even more, let's take another example. This is a very classical problem. M2 now being 0.4 kilograms, which means M2G is 4, right? We assume G is 10. Now you ask the question, is 4, you want to know which direction it goes, right? Now we have 4, before we had 20, now we have 4. Is 4 larger than, let's write it here. Is 4 larger than, what was it? 5, right? This was 5, I wrote it somewhere here. This is still 5. We only changed this now, so I changed this now. Now this is 4. This is the same, and this is the same. So we ask ourselves now in this new problem, is 4 larger than 5 minus f of f max minus plus 4.33. Is 4 larger than 5 plus 4.33? Of course not. So no. It means that the object is not accelerating upwards. It doesn't mean it's accelerating downwards, the first object. First object is not accelerating up the hill. That's all that this means. Now we have to ask the second question. And the second question is 4 smaller than 5 minus 4.33? And the answer is also no. So it's not, the first object is not accelerating down the hill, which means A equals to 0. It's not moving. Okay. At the end of the lecture, I want to emphasize what I started with. First, take your time to digest what you've learned today about friction and the The difficulty with it really is that it depends on in which direction you're moving. The friction is always in the opposite direction. So if you have possibilities in the direction, then you would have the same number of possibilities also with the friction. Plus that the object might not be moving at all. So take your time to digest that. What I started today to talk about was I gave an example with the tires, right, for the racing cars. I don't want to give you the solution for that, but I hope now you understand that the size doesn't matter. For the friction, the width of the tire wouldn't matter. I need to be careful about that, but let's talk about surfaces. The width of the surface, it won't matter. The friction coefficient would be the same. The only thing that matters would be, apart from the materials, of course, would be the angle. So why is it that the tires of the racing cars are normally wide? So think about that. It is related to friction, but it is not so intuitive. The last thing I want to finish with, which I showed you last time, as objects move. Let's see if I can put this here. Objects move. It's not the best angle. It's going around, but at some point it would stop. Later on, we would also learn that there are other forces which are called resistive forces because of the air, which we right now neglecting, right? We're going step by step, and we are developing into more and more realistic problems. It stopped right now. So why is it that using an object like this, which now you really don't see clearly, let me try and so using an object like this, it goes around and then it stops. Oh. Do it here. I use the high-tech one. Goes around, it stops, and then it comes back. Goes around, it stops, and comes back. I'm gonna do it for a third time, and then that might give you a hint. Just look carefully at, or listen carefully maybe. That was a hint. All right. So thanks everyone. I apologize for the what happened today with the electricity, but I think that would only add to your memory of friction that it requires some efforts to go through it. All right, thanks everyone, and until next week. Now all yours.
Hello, everybody. So feel free to take a few minutes to rest, guys. And I'll be back by 2:15, okay? Also, feel free to ask anything in this time. I will stick around, so I will be here responding questions. Okay, hello guys. Hope you're doing well. So I guess nobody has any question, or do you have any question, guys? Should I briefly summarize the key takeaways from the lecture? So in my opinion, the key points are basically understanding directions, okay? So if I have a box on a surface, understanding that friction force is a reaction. So basically, if someone is pulling this box, the friction always opposes the movement. Okay, this would be F, and this would be FR as friction, standing as friction. Okay, friction is always parallel to the surface. Okay, important. The friction is always parallel to the surface. Okay, so if you understand that it's always parallel to the surface and it's related to the normal force, okay, is equal to that normal force multiplying some coefficient. This coefficient normally depends on the surface, okay. You also can relate this to the weight, right? Because this normal force is nothing but a reaction from the weight, from the ground or surface, reacting to the weight of the box, which is mg, okay? So we always relate normal force to weight, and then we can relate this normal force to the friction, okay? And also understanding that friction acts always parallel to the surface, okay? And that normal forces always act orthogonal to the surface, okay? So we can extract the conclusion that normal force and friction force are orthogonal, okay? Hope this makes sense. That's why when you have a slope, okay, as I was asked before with this alpha, and you have this box, of course, the friction is gonna completely depend on the slope. And why is this? Well, this normal force in this case is not the weight, it's not entirely the magnitude of the weight, because the weight is not acting orthogonal to the surface. So we have to decompose the weight first, okay? And once we have W, let's call it X as the component perpendicular to the surface, then we can relate Wx to the normal force. But this Wx is just a part of the weight, which becomes smaller as the slope increases, okay? I hope this makes sense. So if the component orthogonal to the surface is decreasing as the slope increases, the friction force is gonna also decrease, because the friction force is directly related to that normal force, okay? So this is really important to understand, guys, because we are gonna work through it now in the exercises. Do you have any question about this? Wonderful, wonderful. Think about it, guys. It's really important to understand the relations, okay, between weight and normal forces, how, in what direction normal forces act, how do you relate normal force to friction, in what direction friction acts is really important to understand and have some intuition about it before approaching problems, okay? So I would like you to, first of all, when you read the problem, try to sketch it and apply your intuition instead of straight away writing formulations, equations. Just think about it, slow down, sketch it, really important. The sketches are really important, okay? Scientists are every day making sketches all the time. They are so useful to transmit ideas, to understand concepts. So I will start by the assignment. I will cover today assignment number 6. okay? And I will go to the first question, which is, the first two questions are really intuitive, okay? And I just wanted you to have, to solve them by yourselves, okay? So the first one is a ball is dropped from rest and feels air resistance as it falls, okay? So we have this ball, okay? If we sketch all the forces that are acting on the ball, we know that, of course, there is some weight, which is mg, acting downwards. And then we have some friction, okay? Let's call it F. F stands for friction, okay? Of course, it's a vectorial quantity. And we know that the ball is falling, so the acceleration is downwards. What is this telling us? Well, this tells me that the weight is higher, is bigger than the friction force, okay? That's the first thing that I can extract from this. And then I'm asked, which of the graphs represent the acceleration as a function of time? So what did you say, guys? Can anybody provide me some responses through the chat? What do you think? Is A, B, C, D, E? Did you try the exercise, guys? Wonderful, James. You got it. You got it. What was the question? Oh man. Yes, the acceleration is constant. The question is, what was your response to the first question of the assignment 6? That's the question. E. Okay. Let's try to figure out what's going on here, okay? So we know that the acceleration, so what I did is basically, first of all, I say, okay, my summatory of forces, my summation of forces is not 0 because I have acceleration downwards, okay? Why do I know that I have acceleration downwards? Well, I just know that this force has to be bigger than this one, okay? So I have some acceleration, and this acceleration is gonna be equal to the resulting force, okay, which is equal to, let's say, mg. So yeah, okay. Let's see what's going on, okay? So it's gonna be equal to this F minus mg, okay? This multiplying the mass, of course. Acceleration is, okay? Or dividing, because force is equal to ma, right? So then I just, okay, divided by m, okay? So my question is any of those forces function of time? Is any of the forces changing in time? Or is the mass changing in time? Mass won't change in time. Mass will remain constant, okay? So this is my acceleration, right? Well, let's call this Fr to not have confusions, okay? So if mg, g is also constant. So if mg are constant, okay, and the friction of the air is also constant, we will have a constant acceleration. So it makes sense to say that the chart is just constant, that the acceleration with respect to the time is constant, okay? Because neither the forces, neither the mass are changing in time. So the acceleration will remain the same in time as well, okay? Does this make sense, how I approached the problem? So I think the right response is A. Okay, wonderful, guys. Okay, really nice. So let's try to approach the second exercise, okay? And let's see what do we have in the second exercise. I don't know if I'm doing well erasing that. A ball is dropped from rest and feels air resistance as it falls. Okay, it's the same problem. I shouldn't have. So I have this air resistance, Fr, and I have mg. Okay, so we have to know that this force is gonna be, well, we haven't seen air resistance yet. So I think Osama is gonna tackle that later. But we can consider it constant, okay? Even though it might not be. A ball is dropped. So which of the graphs best represents the vertical velocity component as a function of time? Okay, I think you all know the response already, right? We covered it in previous tutorials. Okay, so what do you think? We have constant acceleration because we say that the air resistance is constant. Okay, so if we have constant acceleration, we know that velocity is equal to acceleration, because acceleration is meters per second squared, multiplying time. Okay, so what is this? We are trying to sketch speed or velocity with respect to time. Is this a non-linear relation? Is this a linear relation? Is it constant, everything? So D, wonderful. That's great, and that's completely right. We know that the acceleration is increasing in a linear trend. So we have this. So those exercises are really important because they are very conceptual and they show what is your understanding on the subject. So, for example, if the friction force is related to the speed of the ball, let's say that as the speed increases, the friction force is higher, okay? Which could make sense in a real case, right? So in such case, we will have a decreasing of the acceleration, okay? Because Fr would be function of time. I don't know what function, whatever function of time. And it increases at the speed as the speed increases, because we know that the speed is linearly increasing, or maybe non-linearly increasing, but the speed is increasing, so the friction force is increasing, right? In such case, depending on this equation, the resulting force equal to mg minus Fr, we always have to look at the equations and see if they are linear or non-linear. If, for example, I have non-linear terms here, I'm going to have a non-linear behavior of the speed, okay? So it's really important that you understand how to build the equations, okay? How to relate acceleration to forces, and then take a closer look to the equations, okay? And see if they are linear, non-linear. So if this friction force is constant, this is constant, because nothing depends on the time. If this has a linear relation with t, has a linear, the acceleration will be linear. It will be non-linear if this has a non-linear relation with t, okay? That's really important. So I hope you understand all those relations and you're able to figure it out. So basically what I want to say with this is that I selected in the first part A as the right response, but you can always, it's not necessarily an absolute response, okay? It could be C, or it could be, not C, but it could be D, for example. As long as you explain and justify your answers, okay, you might be right, okay? So if you justify that the friction force might have a non-linear relation with the time, you can justify that the acceleration is decreasing non-linearly as well, okay? Just to mention that. So important, justify your answers, please, guys. 5.10, okay? So what do we have here? We have some diagram, box, force. As you see, always I sketch F1, F2. So you have to know, guys, that you always have to contrast any answer that I provide you, because I don't have the answers. What I solve is not absolute, okay? There is nothing absolute in science, or very few things are absolute. So feel free to discuss with me the solutions, okay? Nobody's providing me with the solutions, so I don't know. So basically you have this, you have some weight here. And you are asked about, okay, let me try to find it. The weight is 60 newtons. So we know that the weight, which is mg, what is 60 newtons. Now we are provided with the value in newtons. What is the tension in the diagonal string? Okay, so this is the diagonal string, and we know we have some tension, which in this case, so if everything is stable, okay, and everything is still, nothing is moving, it means that the summation of forces in X and in is equal to 0, and in Y the same. Nothing is moving, okay? I know that. So then I can start thinking, okay, if I have a force here pulling towards the left, it makes sense that I have a tension here pulling towards the right, and here just the opposite, right? So I will have the tension in those directions. Additionally, if this is in equilibrium, I will have some force here that I will call R. Let's call it R. Okay. So how can I approach this? Well, I can divide this problem, and I can try to get some equations from here and get some equations from here. Okay. So let's call this 1. Okay. And this is going to be 2. So let's try to build some equations, okay? Also, we need angles, 45, okay? So this angle is 45 degrees. Okay, so what does that 45 degrees tell me? Well, this makes my life so much easier, right? Because if I have T here, 45 degrees, and let's say that this is Tx, and this is Ty, well, 45 degrees basically tells me that Ty is going to be equal to Tx. Does it make sense? They are equal. So I start taking some conclusions about my problem. This is important to know. Then I will have to equalize. So for example, I will say, okay, F1 is going to be equal to Tx. Okay, they have to be equal. And R is going to be equal to Ty. I know that Tx is equal to Ty, so why not to say that F1 is equal to R? Why not? Everything is the same, right? It's equal to R. Does it make sense? Do you have any question? Exactly. Wonderful. That's a very good observation, actually. That why are they equal? Well, 45 degrees. So I know that Tx is equal to the absolute value of T multiplying X cosine, the cosine of 45. And I know that Ty is equal to the absolute value of T multiplying the sine of 45 degrees. If I know that the cosine and the sine, that was a great observation. So I know that if the cosine is equal to the sine, it means that Tx is equal to Ty, okay? And you can calculate them by these relations, trigonometric relations, really important, okay? So what else do we need to know? Okay, now we're gonna try to take some equations from here. So I know that W, the weight, okay, is gonna be equal to Ty. Okay, And I know that F2 is gonna be equal to Tx. Easy, right? So I know I have W, so I can calculate Ty and Tx. I can calculate everything here. Okay. So find the magnitudes of the horizontal forces, etc. So we basically know that through this that F1 has to be equal to F2 and that the weight is going to be equal to the reaction or this force, okay, that pulls upwards, okay. And since they form 45 degrees, we can relate them with the horizontal forces. So we can say that all the forces have the same magnitude. Okay. Do you have any question, guys? I don't know if I'm going too fast. Or if I'm doing it right, I might be wrong, right? So. Wonderful, wonderful. My biggest advice for you for the future or for your scientific or whatever careers is that you question everything, okay? Be critic, okay? I want you to be critic with everything. Question everything in your mind. Try to rebate everything, you know? There is no absolute truth and we are here to make some science, right? So what else do we have? 5.31. I think this is a really nice exercise. Okay. So let's make first the diagram. Oh, lovely. Okay, I have two boxes, one on top of each other, one on top of the other, sorry. And then I have someone pulling upwards with a force F, okay? So this is gonna be 1 and this is gonna be 2, okay? So we know that the friction coefficients, so I'm gonna call this M1 and this is gonna be M2, mu2 and mu1, okay? Both boxes move together at a constant speed. That's important. So both boxes are moving together and V, okay, with that speed, at a constant speed, okay, of 15 centimeters per second, the coefficients of the blah, blah. What force do you need to exert to accomplish this? Okay, so we have movement, okay? So first of all, what I would do is I would say, okay, I'm gonna study everything as a system, okay? So let's say that at a constant speed, so there is no acceleration, right? So if we don't have acceleration, what does it mean? Well, it means that the resulting force is equal to 0, right? Together at a constant speed, so there is no acceleration. So we can consider that they are kind of in equilibrium, right? There is no acceleration. So I will consider everything as a system, right? That is gonna be M1 plus M2, okay? And then, well, the first thing that you have to do is to calculate this angle, because I think you're not provided with the angle and you have to calculate it. I hope you all know how to calculate angles, right? So I think the first thing that you have to do is to calculate what is this distance? X, let's call it X, okay? Which you can say, okay, X, this is A, this is B. So X is gonna be equal to A squared plus B squared, okay? And once you calculate X, you can say, okay, so for example, the cosine of alpha is gonna be equal to B divided by X. So how do I calculate alpha? Well, you know how to take the inverse of the cosine, right? Which is the arcsine. So Does everybody know how to calculate this angle with the data that we have? Is anybody having any problem with this? Okay. Wonderful, wonderful, smart people. So I don't have to explain this again. You all know this. So let's assume that you know alpha. Okay. So now the next step. Yes. Do you have any problem, James? Do you need? Okay. So is that a question or? Oh, you know. Okay. Wonderful. Okay. Brilliant. So the next step, once you don't worry, once you calculate alpha, the next step is to sketch the forces acting on this block. Okay. So what forces do we have? So now I'm considering that both blocks, because they move together, they act as a single system. Okay. So they are just one box, which is M1 plus M2. Okay. And now what forces do we have? Well, we have the mass acting vertically. Okay, what else do we have? Well, we have a force acting upwards, F. What else do we have? We have friction parallel to the surface and opposing the movement. We are moving upwards, so we have friction downwards, Fr. And what else do we have? We have normal force acting always orthogonal to the surface, N. Okay, so we know that it's in equilibrium because the speed is not changing. Okay, so we don't have acceleration, even though it's moving with a constant speed, so we don't have acceleration. So acceleration is equal to 0 because the speed is constant. So we know that the system is in equilibrium. So we can say that, okay, what angle is this? Do you see what I point, guys? What angle is this? Is this alpha? Is alpha. Wonderful. So with the sketch and dedicating a little bit of time, you will realize that this angle is the same as this one, okay? It's alpha. And that's a brilliant response. So I can decompose mg. I'm gonna consider x positive, sorry, y positive. So I'm gonna say n. I'm gonna call this w, okay? To make my life easier, guys, if you allow me to. In the question it says that, oh, okay, let me read it again, sorry. Both boxes move together at a constant speed of v. So you're lowering two boxes. I'm not very familiar with the term or the word lowering, but what I understand from this is that both boxes, oh, you're lowering them, so they are moving downwards. Okay, sorry. So in such case, okay, let me draw everything again because I understood wrong the problem, okay? So I'm gonna draw everything again. I'm sorry, guys, my bad. Okay, so they are going downwards, right? Do we agree they are moving downwards? Are they? It changes. It might change some stuff. Let's see if it does or not. Well, I think it doesn't because we sketched properly the forces and we agreed that the system is in equilibrium because there is no acceleration. So we still have a force. We still have a guy or a woman, someone pulling upwards. We still have a normal force. We still have the weight. And we still have friction. But the friction opposes movement, so it changes something. It changes that the friction force points upwards now. Okay. Everything is vectors. Everything is vectorial, okay? So now I can say, okay, so W, so I say this is, okay, so wx minus wx, okay, because we agreed that the x positive is upwards, why not? Or let's make our lives easier. Let's say that the positive x is downwards and the positive y is upwards. Wx, so basically I'm decomposing this in wy plus wx, okay? Wx minus the force of this person minus Fr is equal to 0. And Wy is equal to the normal force. And the friction force, Fr, we know that is equal to the normal force multiplying mu1. Because the system is experiencing this friction, okay? This is what experience box 2 and box 1, but the whole system is not experiencing that. So we have this, okay? So we can say, do we have, so what do we have and what don't we? So do we have the weight? Yeah, we have the weights. So basically the weights are gonna be M1 plus M2 multiplying G. We have the weight, so we have the normal force, okay? So we can obtain the normal force, we can obtain Fx, and we can obtain the friction force. So we can obtain F, we can obtain everything here. Okay, guys? And our time is over, but if you give me 5 minutes, guys, I will solve the second part of the problem, which is really interesting, okay? And it's what I really wanted to cover. Because it's very intuitive and sometimes it's not easy to understand, okay? So basically we are gonna work now with the first box. So this is the second box and this is the first box. So I want to ask you, okay, so can anybody, can we work all together and try to say what forces do we have here and in what directions? So can anybody give me any force that this box is experiencing? What forces should I sketch here? I have normal force, okay? So it's gonna be always orthogonal to the surface. I have normal force, okay. What else? I have mass, which always pulls vertically, mg. What else do I have? I have friction on box 2. Okay, wonderful. But the question is, okay, the whole system, we say is going downwards, okay? So the friction force that this box is exerting on the upper box, what direction does it have? Is it going with the movement or is it going opposed to the movement? So if you intuitively think like, okay, so where is this box trying to move? It's opposed to the movement always, but where is the movement though? So where is this box trying to go? Okay, so we have this. And that's everything we have, okay? So that was everything, guys, just that. Okay, just a little questionnaire. So yeah, it's right, friction is always opposed to the movement. So if this box is trying to move downwards because of the weight, we have the friction force pulling upwards. That's everything, guys. Do you have any other question? I think our time is over. I'm sorry it was short and we didn't have much time. Okay, guys, so feel free to mail me with any question, okay, or any doubt that you have. I will be more than happy to solve and to discuss with you science. So everybody take care. Diolch, everybody. See you guys in the next session.